Hi guys, for my fifth period class, sorry I had to miss class today. Still having some back issues, but feeling a little bit better. We're going to muscle our way through this. And what is this? We are talking about translations, the final of our transformations. We've already looked at reflections and dilations. And now that we have the final one, we're going to put them all together. So we're going to do functions with multiple transformations. So starting with translations, what is a translation? A translation could be equally well described as a slide or a shift. It is just moving the graph some. So the red graph and the blue graph are identical to one another, except every point on the blue graph got moved two to the right and one up. You could think that it got moved straight along this line, but that's a little bit more complicated. Instead, we're going to break that line down into its components and say we moved it two to the right and one up. Or for that matter, we moved it one up and to the right. In this case, order doesn't so much matter. So translations, we're going to think of either as being horizontal, a positive translation being to the right, and vertically, positive being up. So horizontal and vertical ones. How we do it? Well, if I have a function f of x, then to move it to the right by one, I would write it as f of x minus one. That anything talking directly to the x kind of does the opposite of what you would expect. So by subtracting one, you're moving this thing one to the right. By adding one, you would be moving it one to the left. And then if I wanted to move it up two, I could put a little plus two. If I wanted to move it down two, I could put a minus seven or something like that. Hopefully, this kind of rings a bell. Remember when we did the vertex form of a parabola, which looked like A, where A was really just our vertical progression, x minus h quantity squared plus k. The vertex was hk, almost like it got translated h to the right and k up. Oh, wait, it's not kind of like, it is exactly like. That is what happened. In this paragraph down here, which hopefully you read through, we do point out a function with all of those possible transformations. If A is negative, that is a reflection over the x-axis and a vertical dilation by A. If B is negative, that is a reflection over the y-axis and a horizontal dilation by 1 over b. Again, things talking to the x doing the opposite of what you would expect. This has a horizontal translation of x to the right and k up. Again, that to the right and up is kind of assumed. So if I were to look at a function f of x, which contains my favorite point, 2 comma 7, everyone should have a favorite point, minus 2 comma 7, and we applied all these different transformations to it, then what new point would be on our graph? Well, we have to do it in a specific order. That order is we deal with the horizontal reflection and dilation first. So basically, I'm going to take this number and I'm going to divide it by -4. So I'm going to get -1/2. Then I'm going to move it 5 to the right. I'm going to get +4/2. Then I'm going to deal with the y values. My x is going to stay at that +4/2. So first, the horizontal dilation, which is of 2. So I'm going to multiply this by 2 and get 14. And then I am going to add 6 and get 20. So my x value is there at 4.5. My y value is there at 20. I remind you in this paragraph right here, or this little bit, to be careful that they are meant to look like this. If they don't look quite like that, make it look like that. So notice that that 3 is not outside the parentheses. we're going to have to factor it out. So although this might look like it is a translation, a horizontal translation of 12 to the left, once I factor out the 3, oh, no. It was really only a translation of 4 to the left. And that'll sneak back in times. Okay, so looking at probably our most familiar function from the library functions, we are looking at y equals x squared. And in fact, I'm going to graph it. We know it goes through 0, 0, 1, 1, negative 1, 1, and for that matter, 2, 4, and negative 2, 4. It looks a little something like this. If I were to look at a of x, it is a translation of that 5 up, because that 5 is not in the function of squaring, it's outside the function. First we do the squaring, then we do the adding. So every point got moved up 5, including our vertex. It is now at 0, 5. I'm going to go over 1 and up 1 to here and there, and here is that new one, a of x. B of x, on the other hand, that 5 is inside the parentheses, so it's going to move everything 5 to the right. And so here is that vertex, moved 5 to the right. From there, over 1, up 1, back 1, up 1, and something like that. So there is this guy. You don't only have to do a single translation. Uh-oh.
Lily, please come back upstairs and help.
Alexa, hang up. Sorry about that. The next one, we have a translation of 1 to the left and 2 down. So my vertex, yet another color here. Oh, I have one. Here it is. Will be 1 to the left and 2 down. And there is my vertex. Again, the other points kind of follow suit to do the same kind of thing. All right, so there is that one. And finally, this one, we have more than just the translations going on. We also have that reflection over the x-axis and that dilation by 3. So the vertex of this guy is at positive 3, positive 3, positive 1. And instead of going over 1, down 1, I'm going to go over 1, down 3. So we have a narrower parabola over here. And that one is, of course, this one. Okay. Same idea for this cubic function. Let's remember our cube root function. Let's remember it goes through 0, 0. It goes through 1, 1, and negative 1, negative 1. And I usually refer to it as swimmer dude. And it goes out like that-ish thing. I'm not going to do all of these examples, but looking at that first one, there's a little trick, and it's not quite written the way it should be. Let's write it the correct way. I'm going to factor out that negative, and when I do, I end up with x minus 5. The other minus 5 is outside the cube root. Well, this one is going to move me 5 to the right. That one is going to move me 5 down. So 0, 0 moves 5 to the right and 5 down. It should be right there. Well, what about this negative? That negative is a reflection over the y-axis. So instead of looking like this with the top part going off to the right, the top part is now going to go back to the left, just to show you individually what happened. Let's look at the point -1, comma -1, and think of it as, okay, well, it got reflected over the x-axis. So now it is +1, comma -1. Then it got moved 5 to the right. So now it's at +6 and then down. So it's going to be over here. Likewise, the other point, this one right here, 1, comma 1 got reflected, got moved, and got moved down. And it should be 1 up and 1 over from there. Should be about okay, not the best drawing, as it shouldn't be going down at the end, but hopefully we get the idea there. You also have to be careful on D. I'm not actually going to graph it, but let's think of it as the cube root of 1/3 x minus 3 plus 1. If I were to distribute that 1/3 back in, I'd end up with a 1/3 x and a minus 1/3 of 3. Oh yeah, that's that -1. So it does work out. That 1/3 is a horizontal dilation by 3, making things kind of wider. Okay. We've got two different schools of thought on how to think about these transformations. Some people, when they're trying to say, okay, well, what happens to a specific point? They just walk through and go, okay, first we do horizontal dilations and reflections, if there is one. Then we do horizontal translations, vertical dilations, and reflections. And says vertical dilation, which is wrong. This should be a vertical translation. Translation. Who wrote this thing? So that is the order, looking at g of x equals this thing. Again, I did it to my favorite point, 2, 7. I multiplied by -1/2. So I got -1. I moved it 4 to the right. So I got a +3. Then dealing with the y values, I multiplied by a -2 and subtracted 5. So it looks like multiplied by a 3, sorry, this 3 out here, and subtracted 5. So 21 and down to 16. The other way, which we haven't discussed yet, is kind of to reason through, especially in finding that x value. So if I know that f of x contains the point 2, 7, that means that I know one thing. That one thing is that if I apply the function to 2, I get 7. That's all I know. So the only thing that I can apply the function to is 2. So I've got to make sure that -2 times the quantity of x minus 4 is equal to 2. That -2 times the quantity of x minus 4 is equal to 2. That is, after all, the only thing that I know how to plug in to f of x. So let's divide both sides by -2, and I'm going to get that x minus 4 equals -1. And let's add 4 to both sides, and I'll get that x equals 3. Oh, okay. So if I make x equal to 3, then I will be eventually taking f of 2. So I will now reason that I'm going to plug in 3. Now what do I get out? What's my y value? Well, again, when I end up setting x to 3, I end up taking f of 2. And when I take f of 2, I get 7. But I'm not done. What I get out of f, I multiply by 3. So now it's a 21, and I subtract 5. So it's a 16. So if I plug in a 3, I get out a 16. So the point 3, 16 is on there. I wrote this little analogy, just help you visualize what a function does. Oh, it is some sort of machine. We know that this particular machine takes in 2s, spits out 7s. You don't know what else it might possibly take in, whether 2 is the only member of the domain. But I know that if you take in 2, you spit out 7. So I made up this kind of little story about it. You can read through that. Lastly, I thought we'd go through some of this stuff in reverse. I thought we would look at a graph and figure out what transformations occurred to make that graph. Well, looking at this, we get that V. The only place we got a V was when we had y equals absolute value of x. That was one of our parent functions. Y equals absolute value of x had a vertex at 0, 0. This one clearly got translated. In fact, it got translated 1 to the left and translated 3 down. Y equals absolute value of x is a V, but a V pointing downward. This one's pointing upward. Looks like a reflection over the x-axis. And lastly, y equals absolute value of x has a slope of either 1 or -1. This seems to have a slope. If I go over 1, then I have to go down 2. Oh, okay. So this seems like it had a vertical dilation of 2. Now, could I do this with a horizontal dilation instead? Yes, but that's often tricky. So I'm going to say vertical dilation of 2. So my equation is going to look like blank absolute value in the absolute value of parentheses, but with some room over there, absolute value plus another blank. There should be an X right there. We just have to fill in these things. So the reflection over the x-axis, that makes this a minus. Vertical dilation of 2, well, that makes that a 2. Since we don't have a horizontal dilation listed, I could either put a 1 here or just leave it blank. Doesn't really make any difference. The left one means that I do a +1 here, and the 3 down means I do a -3 there. So in case it's not clear, it should look like -2 times the absolute value of x plus 1, all -3. Okay. I'm not going to do the other one. I will leave that as an exercise for you. The parent function here is 1 over x. And it's a little bit hard to see some of it. The center of this thing is at 3, -3 right there, which should tell you something about the translations. Also, I believe it has a vertical dilation of 2, which is a little bit hard to see. So there's a little hint for you. Anyway, thank you for watching, and presumably I will see you guys tomorrow.